Before we even introduce ourselves and get into the weed, we wanted to cover the bottom line up front for this discussion. So data centers have increasingly been now adopting on-site energy generation, like battery energy storage system, natural gas and diesel generators, and hydrogen systems and other microgrid systems. These systems, though, bring the energy benefit for the data centers, they also bring hazards like fire and blast pretty close to the data center. Though these are low frequency and high consequence event, and it can lead to complete collapse of the structure as well. At the same time, it can cause local damage to the envelope, local damage to the roof of the structure. It can cause disruptions in the cooling system, to the power system, bringing in overall disruption of the data center operation. The examples on the right you see shows why this is important. The key message that we would be passing on from this discussion is that these hazards can be mitigated effectively early on in the planning and design stage by using facility siting studies. We can use quantitative risk analysis, effective layout, informed decisions for the equipment placement, supported by the source control, and envelope design and structural detailing.
Just introduce ourselves. And thank you for coming to our session. Alok and I, our background is in protected construction, protective building design. Specifically, our industry is focused on our background is what can happen when you place high energy concentration too close or close to critical infrastructure. So our background is with manufactured explosives, refining, chemical plants, manufacturing. And we're seeing some of the same trends in data centers as this energy comes closer and closer, energy generation comes closer and closer on site. So hoping to share some of our lessons with you. Alok?
Thank you. My name is Alok. I'm the operations supervisor for structures team in our Canada office. I see two of them are from Canada. So very happy to see people witnessing snowfall before coming here. Did you have that? Oh, yeah? Okay. All right, so we'll cover our discussion in 4 frames. Briefly, I know the first part, the trends in the energy solution is all well known to you, but I'll just like to put some numbers and refresh those numbers. Then I will cover the effects of evolution that is coming in the power architecture. And later on, Travis will cover the current structural systems that are being used in the data center infrastructure and what are the response of these structural systems under the blast loads from the hazards that I'll be talking about. And we'll close up with the mitigation part of it. So quickly covering the trends, I know all of you are well aware of them. Some numbers are pretty well etched in your minds being part of the data center stakeholders. The slide on the left, the chart on the left shows the power consumption of data centers in household equivalents. A conventional data center used to consume power equivalent of 50,000 homes. And today we have hyperscalers that is using a power in household equivalent of 5 million homes. So this scale is unprecedented. On the right is another 2 drivers pushing the demand up. One is the GPU cost that has dropped from 2006 to 2024 by 99%. And on the right, we see the demand coming from the AI workload. That has gone up by 350,000 times. And now, where does this power consumption go? In conventional data centers or hyperscale data centers, most of this power consumption is for the servers. And the second part is for the cooling. So these are the 2 components of data center that consumes the power. Combine that with the part that these data centers are almost co-located with urban areas, right, compared to other industries that are far away from it. These two factors are putting a high demand on the grid supply. Again, these two numbers are pretty well known. The current demand stands at 415 terawatt annually, and it is projected to go to 945 terawatt by 2030. It's doubling in just 5 years. And again, we see the same trend. Most of the power consumption goes into the servers and cooling. So this chart basically shows where is this power being generated for. And it's very important to understand where this trend is heading. And that's the reason we are showing this. Globally, most of the power is currently being supported by coal, natural gas, and nuclear. And it is projected to grow in a similar fashion going forward. Only 40% of the demand will be met by the renewable by 2030. And beyond that, it'll be nuclear that will be picking up because of the lead time of making those systems. There are other systems as well that are promising, like geothermal and small modular reactors, but again, the lead time is questionable. United States also shows a similar trend. The only difference being the reliance on coal. It is very less right now, and going forward, it's going to be going less even further by 2035. What's interesting to see is the reliance on natural gas generation and nuclear. The trend from renewables is still around 40%. So to summarize that, the energy demand is increasing 2x by 2030 to 945 terawatt. Meeting this demand from grid is currently a challenge and will remain to be a challenge in next 10 years. The present strategy is to deploy microgrids using natural gas turbines, renewables, and nuclear, of which natural gas and solar with BESS will be the go-to up to 2030, and beyond that, nuclear will pick up and cover the demand until 2035. So what is the effect of this evolution? And just to summarize again, the evolution is, initially we used to have data centers supported by the grid only. Later on, we started seeing on-site generator backup, and then on-site generator backup supported by battery energy storage system, and now we have on-site microgrids. These microgrids have three components: the battery energy storage system, natural gas, and fuel systems, which can be hydrogen, biogas, or natural gas. The hazards that are associated with battery energy storage system is well established. If somebody is from the process safety industry, can vouch for it. These lithium-ion batteries that are used in the battery energy storage system are often prone to off-gassing under heated temperatures. This off-gassing can cause thermal runaways and can have a cascading effect, causing a fire. And typically, in case of a battery energy storage system, once it catches fire, it is said, do not open it, let it burn. If you open it, it's gonna get the air, get the oxygen, and turn into an explosion. So you have to let it burn, which means the fire in a battery energy storage system can last not for hours, can last for days, which is a potential disruption for the data center. A similar case can be shown for the natural gas as well. These generators are typically enclosed because they are external to the data center hall. And any leakage in the natural gas in this enclosure can cause a fill case, leading to a confined explosion. And typically, a confined explosion is much more powerful than open vapor cloud explosion. And then lastly, the fuel systems, which can lead to a vapor cloud explosion, which is nothing but a gas leakage, which will cause a cloud, which can catch ignition from any source and lead to a high pressure and impulse event on to the data center infrastructure. So these are a few of the examples that have happened in the past, which are very relatable to the data centers. This one is from the clean energy power generation in 2010 in Connecticut, where a leakage in the natural gas caught an ignition and led to an explosion which damaged the whole structure nearby. It not only damaged the power generation unit, it also damaged the structure, which is the turbine enclosure. And it's pretty much relatable to a data center infrastructure as well. Here we see a couple of incidents that have happened very lately in 2024 in Otay Mesa. That fire lasted for 6 days, which led to the disruption in the power supply, the power backup, and the infrastructure had to purely rely on the grid supply. Any disruption in the grid supply would mean shutting off the operation of the data center. This incident in Buncefield in 2005 is also a vapor cloud explosion. It was a massive explosion that caused damage not only to on-site infrastructure, it also caused damage to off-site. So even if you have natural gas explosion a little far away from your infrastructure, data center, it can still cause a lot of damage to the data hall. Here we are showing other systems like hydrogen fuel cells or hydrogen electrolysis system. In this particular example, in AB Specialty Silicon, in 2019, there was a leak in hydrogen. This was an indoor explosion. That's why the damage was pretty extensive. But such kind of explosion in the open can also cause damage to the building envelope and the roof, leading to disruptions. With that, we will move on to the structural systems.
Okay, thanks, Alok. Okay, just for background, and what we're going to show here is Alok has demonstrated that when you do bring generation capability using flammable materials like natural gas, hydrogen, or storage systems like battery energy storage, you do present the possibility of having high hazard events nearby to your facility. This most likely is not always a design consideration when designing or siting a data center. However, in our experience, each time in history where we try to centralize high amounts of energy in one location, we do have these events. So there are safety systems in place, but safety systems can fail. They don't always perform the way that we intended them to. So what we're going to demonstrate here is just measures that can be taken to mitigate what could happen. And I'm going to start with demonstrating what systems we're typically using to design data centers and how those systems typically respond to the hazards that Alok's already talked about. All right, so first of all, just data center building construction or structural design in general. Just looking out from an outside view, there's multiple types of construction that are used for data centers. Pre-engineered metal building, like a steel frame with an insulated metal panel, is common. Probably the most common is going to be a steel frame with precast concrete or tilt-up concrete. But also seen, just again from an outsider's view, could be some form of modular construction. I'm going to introduce, just for our discussion here, this idea that any type of building construction has some form of inherent capacity, whether that be in capacity to a thermal event or capacity to a blast event. In the Alok and I's industry, we represent this capacity through these curves, which represent the capacity of different types of construction to different blast loads. What you need to take away from this is that more blast causes greater levels of damage, and different types of structural systems have different types of capacity. And some of that can be almost logical, right? That a metal building would have less capacity than a concrete building. Let me go back just for a second here. The next thing I want to show is Alok introduced that there could be vapor cloud explosion from a natural gas generator. There could be a fire/explosion threat from battery energy storage, and there could be explosion/fire risk from hydrogen. He demonstrated that there has been events in industry where these things have occurred, maybe not always at data centers, but they have occurred in industry. I'm now just going to demonstrate what these could look like based on the work that we have done at our company through testing. So Alok presented real life situations. I'm now going to present situations in testing. Some of these videos have sound, so I'm going to let the sound play through, and then when the sound is done, I'll continue talking. The video here is an example of what could be generated from a vapor cloud explosion. For our reference here, this would be a case where there is a leak from the gas supply or fuel supply into the generator that gets out in the open air, finds an ignition source at the generator, and then explodes. For the demonstration here, what we're showing is just that there is a hazard to, in this case, personnel or equipment that would be located in a building near the hazard. Series of videos here is from an example of what could occur in a battery, I'm having a hard time saying that in three words. Battery energy storage container. This is, again, a test condition that we've replicated. What we've done is we have filled a container that represents the container that we use in the BESS with a concentration of fuel similar to what could occur if you had a thermal runaway inside the container. Again, just demonstrating there is a fire hazard and a possibility for an explosion hazard when these are located near occupied or critical areas. In this last video would be representative of a hydrogen event. So this video may keep on playing. This would be representative of a hydrogen event. Again, in industry, we have heard of some projects that are looking at the possibility of using hydrogen as a clean source of energy to fuel generators or backup generators. So again, bringing this type of fuel on site presents a more severe hazard than using a natural gas, with loads that could be applied to the building structure that are much greater than what would be relevant for natural gas supply. So what we demonstrate here is that if I take the loads that were produced from our test and apply those to those capacity curves I showed 4 or 5 slides ago, what we see is that for each of the cases that we talked about, they have the potential to cause more than structural damage, but potentially structural failure to components that are typical at data centers, whether they be insulated metal panels, precast concrete, or tilt-up concrete. The possibility is there for events that have happened in industry and then we've replicated in test conditions. I'm going to switch gears here for just a second and talk about, instead of blast, talk about fire, but the idea is the same. Some of these events not only can produce a blast hazard, but can produce a fire hazard. Alok talked about the BESS condition where you can have hours of fire. There's also the possibility that instead of having an explosion from a gas leak or a hydrogen leak, you transition to a fire. Again, some of this is common sense, that concrete structures would have more resilience than a structure made of lightweight insulated metal panels. And that's what this video is showing here, that there is the temperature rise inside the building is less when you use materials like concrete versus steel construction. Okay, and then as we transition to, okay, what do we do about it? Just making one more point, that these events have occurred. The events that we're talking about right now are on the accidental side, right? That you're not intending these things to happen. But we have seen, as Alok pointed out in this first slide, some intentional events from some bad actors that have also caused downtime or significant interruption. So these are events that have occurred, and as more and more data centers come online, there's more and more energy moving closer, it's our expectation, our forecast, that these events would become more common. Okay, so now to maybe to the meat of what we're talking about. What are you supposed to do with this? It would be nonsensical to design all your data centers for these worst case events, because the cost of the data center, the time to get up to speed, would increase substantially, right? So the clients we serve in other industries, we provide the same advice. Our advice is not to design for these worst case scenarios and spend hundreds and thousands and hundreds of millions of dollars reinforcing or making your construction stronger. There's a logical process that needs to be taken to make sure that you have coordinated your design with realistic events and make sure you're providing the protection that you need. And so that's hopefully, over these next few slides, the point that I want to get across is we've demonstrated that industry is moving to this point where there's more on-site power generation. By moving that on-site, you created some hazards on-site that previously were not there. We've demonstrated these hazards can cause damage. That damage can result in downtime and financial loss. Having said all that, we now want to propose what could be done to mitigate those hazards and mitigate those loss situations. Like I said, it is not advisable, in our experience with working with data center owners and operators, that you design all the buildings to resist the loads that we showed previously. But it's our experience that working through a process of planning, siting, and design can create a situation where you've mitigated or removed the hazard and then minimize the out-of-pocket expense that needs to be spent on reinforcing or intentionally designing structures. Some of this has been some of this idea of reinforcing structures, just make the quick segue here, has been going on for several years. A lot of in previous, let's say 10 years ago, the idea was more from an anti-terrorism standpoint, that you could have a bad actor on site that could approach the site and implement a ready-made bomb close to the facility, and so you wanted some inherent protection against those events. It's the same idea with what we're going to talk about here, that when we were talking more from an anti-terrorism standpoint for data centers, you didn't want to reinforce all your buildings for the worst case bomb, but you wanted to be strategic, that you wanted to have fencing around your perimeter that kept people away. You wanted to make your structures to where they weren't easily recognizable. That way people didn't target a big sign that said data center owner here. So you did engineering controls, you did passive measures, and then when those things did not work, then you spent money on reinforcing the building structure. It's the same idea with the accidental scenarios that Alok and I have been talking about today. When you're looking at your hierarchy of controls, the first thing you want to do is remove the hazard. The second thing you want to do is put in engineering controls that mitigate the hazard. And then lastly, you want to spend money on engineering design that mitigates the hazard. So let's just walk through a couple of those. This is not a data center. This is another project that Baker Risk has worked on where there was a potential for explosion. The idea here is creating distance between what is the hazard and what you're trying to protect is your best means of protection. The same idea from a terrorist threat, right? If you can put a fence between you and the bad actor, that's the best way to protect yourself. So logically thinking how this apply for a situation in a data center, providing offset between the generators or the BESS and the data center, even in 5s and 10s of feet, could buy you significant levels of protection. What we've done here is prior to construction, prior to design, run through an analysis to see what could happen, and then based on the results of that, inform the layout of the facility and then ultimately the design of the facility. But taking these steps very early in the process removes the possibility, could remove the possibility of having to reinforce the building structure. The next thing we'll talk about, so you have the early study, you figure out what your hazards are and site your facility accordingly. The second step is to think about how you're going to lay out the facility. So there are opportunities for some of these hazards to place obstacles between the battery, the fire or blast hazard and the building you're trying to protect. Again, this is could be a low-cost measure. You've offset it to the distance you can offset it. Now placing barriers or barricades around the hazard could further protect the building structure. Again, these are early decisions that can be made well before design and definitely well before construction that then can be implemented in design and in construction. Then you have the idea of a source level hazard mitigation. I'm going to talk specifically of like a BESS container here. That we know there is the possibility inside the container that you could have a thermal reaction, a thermal runaway that occurs. When that occurs, you could have off-gassing of flammable material inside the container, generate a flammable atmosphere inside the container, and then either turn into a fire or an explosion. Most BESS containers now are equipped with deflagration vent panels to relieve pressure inside the container prior to that disastrous video that we showed earlier occurring. These are source level mitigation measures that can be implemented to reduce either the consequence or the frequency of the event occurring. Other ideas that have been implemented in other industries would be automated shutdown of gas supply, of hydrogen supply in the event of a release, early detection, early isolation, are all things that can be done to mitigate the hazard at the source instead of trying to mitigate the consequence of the hazard at the building. And then finally, we arrive at what can be done to the building structure. This is Alok and I's background. Alok and I are both structural engineers. And when those other measures are not enough, this is where we have stepped in and provided protective design for the building structure itself. Most of our experience when doing these projects is in the precast or tilt-up concrete construction. So you're looking at the envelope of the building. Like I said before, precast concrete or tilt-up does have inherent capacity for the events that we're talking about. So typically the enhancements we're making to the structure are not extreme, but they are made to where there is additional capacity of the panel and then additional capacity of the connections between the panel and the building structure. And again, the reason we're doing this is to minimize the loss of the building structure, and then also to hopefully protect the equipment inside the building from one of these events that could occur. Other things that we often look at on these projects would be things like if there are windows, especially in buildings that could be occupied on the data center, or building doors, making sure they're enhanced or designed to protect are designed to resist the loads that we've come up with. In general, that's where our work has stopped, is looking at what we call the fenestration of the building or the envelope of the building, the things you would see from the outside. However, there have been projects we've worked on where we've continued to enhance the building structure just due to the magnitude of the loads. Let's say, for example, projects that have hydrogen on site would have a higher load, higher blast load than natural gas. So for those types of building structures, the work we have done is, in addition to enhancing the fenestration, also looking at the building frame, the building structure, and enhancing that as well. And again, the reason we do this is because we're trying to protect what's inside the building from being a loss in one of these infrequent events that could occur outside the building. Okay. As we close here, I want to go back to what we started with at the beginning and wrap up in conclusion. That it's, I think, a localized opinion that this is a new topic, or could be a new topic to this industry. Our effort in this industry on this topic specifically has been growing, but I don't think this is a concern that most data centers, when they're being designed and constructed, are considering. Yesterday, we said in a couple presentations more from the insurance side, and some of these concerns were raised there. We know from our experience, again, that some of the manufacturers of generators are being asked to consider these hazards when they're supplying their product. But as far as where all those dots connect, I think it's very early in trying to figure out where this all connects. So our intention today was to introduce a topic, to show that this is a real hazard that we have seen in other industries outside the data center industry. But some of the trends happening in the data center industry are lending themselves to bringing these hazards closer to property of the data center, but also closer to consideration for offsite as well, right? That data centers are located closer to occupied urban centers than typical power generation sites are. So hopefully the lesson to take from this is early study of what the hazards could be, is really the idea to minimize the cost of implementing controls. By understanding what the hazards are from a fire and an explosion standpoint, engineering controls like standoff, engineering controls like barriers can be implemented at the source. If those do not suffice, then controls like envelope protection and protective design can be implemented at the data center level to protect either occupants or the equipment inside the building. Alok, what else?
I think we've covered
closing here.
every aspect of what people should know.
And as we've come to the end of our script, I realize we're ending with a few minutes early before the time is allotted. So if we have questions from the audience, we can take questions. Yes, sir.
I think you just already alluded to it here at the end, but I was curious on the engagement of such analysis pre-project. It sounds like it's in its infancy, right?
Yeah, yeah. I would definitely say it's in its infancy, and I would definitely say it's the big players that we see asking the question. But I'd definitely say it's in the infancy. Drivers that we see is when there is consideration for a hydrogen source or hydrogen fuel being used. And I think that leads to looking at other sources as well. So that's one from the owner side. And I do know that, like I mentioned, some vendors are being asked to at least provide consideration for what could happen. But again, I couldn't give you a percentage, but it's very early adoption.
Yeah, I was just thinking about the AHJs as this begins to really develop, that there's going to be more need to satisfy, obviously, you have the NFPA up here, and those codes and standards are the best. There's a lot of stuff in NFPA right now, right? I mean, they've really done some. Yes,
in the past several years, we've come a long way.
More, again, engineering outlets.
Yeah.
This is
Yeah, when you look back on history, right, you have events and you have technology that always exceed what the engineering controls are in place. But those things are always slow to catch up. And sometimes it takes events to occur to make the controls to speed up. But I definitely think we're heading in that direction. Yes, sir. I'll come to you. Yo, you first. Sorry. Front row.
How well is the industry, the data center industry, accepted the damage limiting construction?
How well have they?
Yeah.
Yeah. Again, I know from experience that it's being adopted in some locations. Again, I think on a historical front, 10 years ago, a lot of this damaging limiting construction was more from a bad actor scenario, that you had a potential for a bomb or a ballistic threat outside the property. So that's where it started from. But here in the past 5 years, we have seen I know of multiple cases where there has been protection built into the building to protect from an accidental explosion on site or an accidental fire on site. So I think the answer is similar. It's in an early adoption, but I know it is occurring. Yes, sir.
So as we're seeing a lot of companies talking about DC and bringing DC into the data center, one of the things that has also been discussed is the implementation of like capacitor banks and things like that right at the rack level. So I wanted to see if you guys have started doing investigations on what the implications for safety and blast. I realize this maybe is more like an NFPA 70E or an NFPA 70 sort of a question, but they would behave differently than like a battery.
Right.
And the fact that you're going to distribute that with all your IT equipment, I sort of want to know what your thoughts are, or if you guys are doing research on this, or if this is something that you guys are where you're at.
Yeah, that's a great question. Let me first of all say, Alok and I have been drinking from a fire hose all week, so we're definitely coming up to speed of where industry's at. We as an industry or as a company had talked about like arcing hazards, transformer hazards, not at the data center level though. That's typically from our clients at an industrial level. But that to me was a red flag of what could be occurring at the data center as well, that we need to be looking at that as well. So yeah, I would say very early, for sure. Yes, sir.
Yes, thank you. There are two sort of big trends that I've heard a lot here at Data Center World. One is like the massive increase in investment in BESS systems for sort of grid management. And the second is a lot more sort of prefab modular deployments that we're seeing. I'm curious to know the fact that you're talking about that this industry is still in its infancy around sort of blast and fire safety and hazard. Do you see that being integrated into some of these like modular designs and prefab, or do you think that that's kind of a gap in what some of these big system integrators?
Yeah.
Is that a gap in their sort of design systems?
Yeah. I think it's from two fronts, right? It's from what the generator of the explosion or fire could be, as an example, the BESS, and that's definitely incorporated at a modular level. That these systems like deflagration vent panels, or source mitigation can be at the BESS level, and that's definitely we're seeing a modularized trend. It depends, I guess, on the size of the data center. But from a protective standpoint, I think there is opportunities for modularization too, especially at smaller data centers, or if you're using components like precast that are coming out on site already ready to assemble. So there's definitely opportunities for modularization. Any other questions? Well, I appreciate y'all attending on day 4 of the conference. Thank you for sticking around. If you have more discussions, would love to have that. For those of you who ask questions, stick around. I want to get your card. Make sure we continue to talk. Thank y'all.